Dobra, cześć wszystkim. Wracamy po bardzo krótkiej przerwie i przedstawiam Wam Rafała Wysockiego z Kernela Linuxa. Opowie nam o kontroli termicznej w Linuxie.
All right. Thank you. So hello, everyone. My name is Rafał Wysocki. I'm a kernel developer, a Linux kernel developer. I am also a Linux kernel code maintainer. So I started to contribute to Linux in 2005, and I've been maintaining some pieces of kernel code for like 15 years now. And the thermal subsystem in the kernel is one of the pieces of code I maintain, but I've been doing that for a relatively short time. So this is what I'm going to talk about today. I work at Intel as a principal engineer right now. I work on the Linux kernel mostly, and things related to it more or less. But I have to say that I don't speak for Intel. And if you and the opinions expressed by me are mine, and if you want or need the official stance of Intel on anything, you can ask by in a proper way, and asking me about it is not the proper way. So, okay, so that's a formal part. And all the materials in the presentation are mine too, and it was created with open source software coming in the distribution I use, which is OpenSUSE. All right, so this is going to be a technical talk, but not very deeply technical. So I'm going to omit a lot of small details that. Most related to the implementation. And the implementation has been in flux for some time, like for several kernel releases, so the details are not worth talking about anyway because they change. All right. So thermal control. Thermal control is important, and I hope I don't have to convince anyone about that. And it is pretty much all about heat management. So it is good to realize that heat is the kinetic energy of the chaotic motion of particles, and it's important. So because it is chaotic, this motion cannot be controlled directly, and the way to control it is to control the flow of energy in and out of the system. So, okay, the illustration photo was taken in Lisbon, Portugal, in 2019 on a very hot day, and you can see in it some people spending time next to water or close to water. And actually, they manage heat in their bodies this way because water evaporation extracts heat from the air and next to it, and then the colder air helps them to extract heat from a human body. So this is an example of heat management, surprisingly enough. All right. Heat changes properties of materials, so that can be used to build devices to measure the amount of heat, which is reflected by temperature, obviously, right? So these are thermometers in my office. I mean the ones in the photo. The one on your right is the mechanical one. There's some piece of metal that bends more or less depending on the amount of heat in it. The one on your left on your left is an electronic heating controller. Actually, it controls floor heating. So the ability to measure temperature is key in this exercise, because if if you want to control something, we need to measure it, right? So in order to manage heat, or to keep heat in check, we need to measure temperature. We need to be able to measure temperature, and this ability has to be provided by hardware. Essentially, that there need to be thermometers in hardware. By the way, the thermometers that are built into electronics are mostly or often referred to as thermal sensors, but they are thermometers anyway, right? Okay, so thermal sensors. Sorry. One of the ways to keep heat in check is to define temperature levels at which some actions will trigger, right? So something will happen in response to the temperature reaching a certain level. Such temperature levels are referred to as trip points. And this is okay. So the photo is Warsaw West railway station under reconstruction, and then there is a bridge in it. I'm not sure how well visible it is, but in brown somewhere here there's the bridge, and you can imagine people walking the bridge from left to right, and say that the goal is to prevent them from reaching the far end, which is somewhere here, right? So and there are stairs above every platform. So say we would instruct some people to go downstairs when they reach the stair, here or here or here. So this is like a model of a temperature sensors with sensor with trip points, right? And on every trip point we take some heat, some energy away out of the system, and that it works in analogy with this. Okay, so trip points. This is not intuitive, sorry about that. So that when we have trip points and we have those actions defined, what to do when the trip point is crossed on the way up, by some temperature measured by some thermal sensor. So this can be used to represent a thermal zone. So thermal zone is some volume in the system in which the temperature is approximately constant, like the same. And there needs to be a sensor measuring it, and when we add trip points to it and some mitigations. So thermal mitigations are the actions taken to cool down the thermal zone. When we have all of that, we can define a thermal zone, and the way to register something like that in the thermal subsystem in the kernel is to call one of these two functions here. Come on. Oh. This is for the regular one with 3 points. The other is for a thermal zone without any 3 points in it, which is also useful because it can be monitored by the kernel. So if you have a thermal sensor without 3 points and a driver for it, which can just extract the temperature value from it, it can be registered as the tripless thermal zone. And when a thermal zone has been registered, the contents of it, so all trip points and also cooling devices bound to it, which I'm going to talk about in a minute, become visible under sysclass thermal in sysfs. Okay, so I was talking about the sensors, the trip points, and what about the actions or the mitigations? So they are represented by 3-point types. There are 3 points of different types, and I will get to that in a minute. And there are cooling devices. So cooling devices are things like fans and, I don't know, liquid cooling things, and also software devices that are used for cooling, and more about it later. So we have to bind cooling devices to 3 points, and then use, when those bindings are defined, and we have mitigations defined as well. Okay. All right, and how this works, or how does this work? First of all, there are 4 types of 3 points defined. There are critical 3 points, hot 3 points, passive and active 3 points. Okay, so critical is the most straightforward thing. If the temperature passes the critical 3 point on the way up, the system is shut down. Very simple, or rebooted depending on what's best for it. Hot 3 points are similar to critical, so the action to carry out in this case is to hibernate a system or suspend it so it doesn't do any work and then doesn't heat up, and let it stay in this state for some time so it can cool down. Passive 3 points are 3 points that for which the devices, the cooling devices, are passive, or in other ways they throttle components of the system, like CPUs or GPUs or similar. They just reduce the frequency or do something like that, and those are mostly software devices. They are not pieces of hardware, but some algorithms in the kernel that know how to reduce, say, a frequency for a processor or something like that. So this is called passive cooling. So passive cooling, or throttling, or reducing the capacity of compute components that draw less power and spend less energy when those cooling when the throttling is applied. Active cooling devices, on the other hand, are very straightforward to understand. They are fans and similar things, like things that take energy away from the system, generally speaking. All right. The binding between a 3 point and a cooling device is represented by an object called a thermal instance in the kernel. It is something that defines the minimum and maximum temperature, not the temperature, minimum maximum state for a cooling device. So the cooling devices have states, like between 0 and some maximum number, and they can be put into one of those. So the thermal instances contain min and max states for each device bound to a given 3 point, and a weight of it, which is how effective the device is in cooling down the thermal zone. All right, so the whole picture is that we have a thermal sensor, then we have 3 points for the temperature measured by it, and then for each 3 point there is the number of cooling devices bound to that 3 point that are used to cool down the thermal zone. Now the question is, okay, how this all works? So there needs to be a component that will somehow select the states of the cooling devices. And yes, there is such a component, which is thermal governors. And then, when I say governor, you think, oh, this is like we picture a man in power who tells everybody what to do, like the guy on the monument here. Again, this photo was taken in Lisbon, Portugal in 2019. But in the thermal subsystem in the kernel, actually, governors are very simple. They are simple pieces of code that select target states for cooling devices. They just pick up the states using different criteria. There are like 5 governors. Each of them works in a different way and uses different criteria. And then we need to choose one for a given thermal zone. And now, OK, so who decides what levels of temperature will be the trip points? How many of them there will be, which of them will be active and passive, and then what governor to use. So this is a platform firmware in the majority of cases. Because you need to know how the platform is designed, what components are used, how much energy they spend, and so on, right? For that. So in the majority of cases, the information on how to set up the thermal zone comes from the platform firmware. So we have the information from the platform firmware. It is used to register a thermal zone, register cooling devices, bind everything together, and then use a certain thermal governor to select the target states when the trip points are crossed on the way up. I have to. OK, so now say we have the simplest possible situation that we can imagine. So we have a thermal zone with 1 trip point, with a cooling device, which is a fan, active cooling device, and a governor, which is, again, very simple and works by turning on the cooling device when the trip point is crossed on the way up. And then it turns the cooling device off when the trip point is crossed on the way down. So this is the diagram on your right. OK, and let's see what can happen in this case. So say the temperature is growing. It crosses the trip point on the way up. And now the cooling device is turned on. So the temperature starts to fall down, and it crosses the trip point temperature on the way down, and the cooling device is turned off, and that repeats like in a loop. So effectively, in this case, the temperature of the thermal zone will stick to the trip point temperature level unless something else happens, like the workload changes or something like that. So that may not be desirable, and in many cases we want the temperature to really fall down well below the trip point level, and then for that trip point hysteresis is used for that. And the way it works is illustrated in the other graph. So in addition to the trip point temperature here, we have a hysteresis value which is subtracted from it to obtain the low temperature of a trip point. And the way it works now is that when the low temperature is crossed, nothing happens until the proper temperature is crossed on the way up. Then the cooling device is turned on. Now the temperature hopefully starts to fall down, and then it crosses the temperature of the trip point on the way down, but nothing happens until it crosses the low temperature of the trip point on the way down. And that's the point where, or at which, the cooling device is turned off. So the cooling device is off when the temperature is growing in this hysteresis range, and then it is on when the temperature is falling in this range, right? So it allows the thermal zone to be really cooled down below the trip temperature value. Okay, we have all of that. We have sensors, trip points, cooling devices, governors, and everything. There's one more piece still. that needs to be present, which is the monitoring. So the thermal zone needs to be monitored in order to notice the temperature changes, obviously, and it can happen in a few ways. There is a you can define a thermal zone to be monitored by the kernel periodically, so the kernel will read the temperature periodically and see, how it changes. There can be hardware support for it, so the hardware can notice that, oh, the temperature has changed, and it may be programmed to interrupt the CPU when a trip point is crossed, for example. And there is one more way, which is called passive monitoring, which is when a passive trip point is used, and then the kernel uses a special monitoring, special polling mode for this case to notice when to apply throttling. Okay, the illustration photo is a place in Warsaw. And it may not be entirely visible or readily visible, but there are cameras on these pillars here, so it is monitored all the time. Okay, and that's pretty much what you can do with the kernel's thermal subsystem. You can register thermal zones, set them up to be monitored, set them up with trip points, with cooling devices, tie all of that together, and enjoy your thermal management, thermal control. Sorry. It is good to know when things work, when they don't work, and for this purpose, there are facilities, monitoring facilities for this. So user space can subscribe to messages sent on certain events from the thermal subsystem via netlink, which is an inter-process communication facility used for many purposes in the kernel. So this is a list of different events that can be signaled through netlink from the thermal subsystem to user space. And obviously, each of them is associated with a thermal zone. And there is also a diagnostic facility that can be used to monitor a thermal not to monitor, but to check if the thermal control works or how it works. The statistics are collected and they can be looked at through debug.fs in this directory, which has statistics for, or holds statistics for thermal zones and cooling devices. And this is a new feature, so you need a kernel version 6.8 in order to use it, and actually in 6.8 it doesn't work really well, so you'll need a very recent fix to make it work, but in 6.9 it should be much better and then usable. So okay, so you can use this to see if how thermal control works and if it works as expected. Okay, so that's pretty much all the kernel can do in terms of thermal control, but it may not be sufficient. So the thermal zone-based approach is reactive, so it reacts to events when the temperature crosses a certain level, and then we do something, right? The modern computer designs, or not only modern system designs are often thermally challenged, so they don't contain or don't include any active cooling, for example. No fans, no mechanical parts, stuff like that. So energy actually cannot be moved out of the system easily. It has to flow from it in a natural way. And so the only way to to actually manage heat in those cases is to prevent excess energy from going into the system. So we have to reduce the power draw of the system. The tram in the photo it goes through also from time to time on holidays mostly, and it is, you know, on a hot day. It doesn't have any air conditioning or anything like that. It's just windows and openings in the roof. So on a hot day, it is really thermally challenged. So yeah. Now the effect that we want to counter in this case is the accumulation of heat, which happens when there is a lot of excess energy in the system, and it gets to inner degrees of freedom on it, or particles somewhere deep inside of it, which start to vibrate, and then it takes time to get energy out of them again and pull it out of the system, or rather let it flow out of the system naturally. So again, the way to deal with that is to prevent excess energy from going in. So the photo is an illustration of the accumulation of heat problem. So this is Rangitoto Island in New Zealand, which is a dormant volcano that appeared like 500 years ago or similar, and it's from the geological time frame standpoint is very new, like a very young thing. There is a lot of lava turned into stone, like the stuff here, which absorbs energy from sun and heats up a lot, so it gets hot to touch even, so it accumulates a lot of heat, and we don't want anything like that to happen in a computer, obviously. So the way to manage those cases is to actually avoid reaching a tree point. Like instead of reacting to crossing it from when it's crossed on the way up by the zone temperature, we actually try to predict when it will be reached, and there's some facility that prevents it from, or software entity, I should say, that prevents it from happening. It's kind of a balancing act, like walking a rope, which the animal in the photo is doing. So the photo was taken in San Francisco in 2013, actually almost 11 years ago. Again, I'm sorry. There are hardware interfaces that can help in doing that. And this is an example of one of them, which is called running average power limit, or RAPL. And that works by applying an average power limit to in a certain time window, or a time window of a certain width. And so in the diagram there are two time windows, or rather two widths of time windows. One is T2, which is a shorter one, and the other is T1, which is the wider one. And we set the average power limit for each of them. So the average power limit for the narrower time window is twice as high as the one for the wider time window. And now the part on your left is on your right, sorry, is again is showing that what happens if maximum power is used, or maximum energy is spent in all of the shorter time windows in the first half of the larger time window. So if we go for the maximum power or maximum energy, then we have to stop spending any energy in the middle of the wider time window, and then the component to which this limit is applied needs to stay dormant. You cannot do anything in the second half of it. So in order to avoid that, it is better to allocate energy or power in a more like to distribute it more evenly, like in the second half of the graph. But using this to control heat or manage heat is kind of convoluted, because in order to do this, you need to know the relationship between the power limits and how much excess energy there will be there in the system. So again, this information needs to be provided by, say, the platform firmware, and it needs to come from somewhere. There is a piece of software which does this, which is called Thermal D, or the thermal daemon. It has nothing to do with Maxwell's daemon, and it works in user space by trying to predict what controls to apply in order to prevent the temperature from reaching a certain trip point, or a set of trip points, actually, because for different thermal zones. So for now, or at the time being, Thermal D works on systems based on Intel chips, but in principle it can work for systems based on on chips from any vendors. And it uses RAPL and other interfaces related to power control in this exercise. All right, so that's all I had to say today. So thank you for attention, and are there any questions?
Is throttling handled by kernel or CPU?
It's throttling handled by kernel. So the kernel sets the maximum frequency limits that then are observed by the CPU. So you can say both, right? So the kernel sets the limit, and then the CPU has to adjust to it.
Many PCs allow to set thermal zones in UEFI. Does the kernel respect those? Does it override them, or what else happens?
So it generally does respect those. So the problem is that the information regarding thermal zones comes to the kernel from the platform firmware through ACPI, which is a different interface than UEFI. So if you define the thermal zone in UEFI, the information has to be translated into the ACPI information, and then the kernel can retrieve it from the platform firmware. If that works, then the kernel will respect the setup, but it depends on the platform firmware.
Do you have any recommendations on thermal setup configuration when measuring software performance?
Measuring software performance. That's a tricky one. So let me say this. On all modern systems, I recommend to use Thermal D, at least in the Intel-based chips case, because it can retrieve information from the platform firmware that is not used by anything else, and it can very precisely tune the system to to the given conditions. So use thermal D. Now, if you have to or want to go up with performance, okay, so the rule of thumb is this, that at one point the hardware will start to protect itself from damage. And if you reach that point, then it's going to be very drastic. So it will slow down a lot, and it will pretty much go to a halt. So you want to avoid that. And as I said, the best way is to use thermal D, and you have to know that what happens when you like go too far.
Why open SUSE?
Why OpenSUSE?
SUSE.
Okay, so that's an interesting thing. So I have a sentiment for it. I have to say at one point. So I used to be a sysadmin at the University of Warsaw Faculty of Physics, and then OpenSUSE was the only distribution that worked for me in the faculty. So I could do everything I wanted with it, and set it up so other people could use it. So, and since then I've been using it.
Okay, and there is a hot question. I just did cat sys devices virtual thermal zone 1 trip.1 temp and got, what is that number? 150. How much Celsius degree is that? How do you calculate it?
So if I remember correctly, it is in millicelsius. So you have to divide it by 1,000.
You know what to do.
But as I said, if I remember correctly, it may be micro Celsius, but yeah, I think it's in millicelsius. But anyway, it's in a fraction of Celsius degree.
It's weird, but it could be 100. Okay. What if CPU has multiple temperature sensors and they provide different readings?
A computer can have multiple different sensors, and then for each of them there is a separate thermal zone. And each thermal zone have a different set of cooling devices associated with it or bound to it, and it has a different thermal governor maybe.
Is it possible to define own thermal zones with own actions happening when they are reached?
Yes and no. So on a PC, it is not possible right now. On a system that uses a device tree as a platform firmware, it can be done. And there are cases when drivers register thermal zones and then they allow trip points to be modified by user space. So, yeah. Multiple answers, I suppose. It's not like one yes or no.
What is DPTF and why are its configuration values proprietary?
What's DPTF? The TLA stands for Dynamic Thermal and Power Framework or something like that. And it has been invented, I should say, at Intel at one point. By people who were mostly considering Windows as the target use case, and they thought that they would be able, or rather, they wanted to avoid exposing their algorithms to other people, and that's why they decided to do it, to make it proprietary. But as far as I can say, this is changing now, so we'll see.
Are those photos yours?
Yes, they are. I said that already.
Do you know how well the handling of performance and efficiency cores of new Intel CPUs are implemented in the kernel with regards to thermal cooling?
Can you repeat that? Sorry,
Okay. Do you know how well the handling of performance and efficiency cores of new Intel CPUs are implemented in kernel?
For new Intel CPUs, actually, as I said, thermal D is a way to manage those, and not the kernel. The kernel has because those systems are all thermally challenged, no matter what. Then the kernel is not like too simplistic for thermal management of those things. Thermal D.
Are some new thermal features available in Linux Intel branch? LTS branch.
Intel branch. I don't know what you mean by Intel branch.
I don't know too. That's the question.
Okay, so I guess so I can probably answer this, but if the person asking this question could send me an email to Rafał@kernel.org and ask it, and then we can talk. And so are you referring to Clear Linux possibly? So that is mostly focused on performance and not on thermal control. So I wouldn't expect any. So there is thermal D has is hosted on GitHub as well. So I would go there instead and see what's there, because it should be it should support all of the new Intel SoCs. But you have to take the latest version from GitHub for it.
Any comment on how Jetson handles thermal control?
How Jetson? No comment.
Okay. Okay. There are no more questions.
No more questions. Okay, so we are ahead of time. Thank you very much again, and I hope you enjoyed it. And yeah, have a nice day. Thank you.
Thank you.